There we go. So, uh, yeah, today we have Kirill joining us, and he's going to present on action matching. He's at the Vector Institute with Ali Reza, who we heard from before and seen great work, and working with Rob and Daniel, who we heard other presentations from. So, thank you very much, Kirill. Welcome, and take it away.
Yeah, thank you, Alex, for the introduction. So this work is we call action matching, and this is the joint work with Rob, Daniel, and Alireza. And I would like to start with this picture because Daniel told me that like a lot of people there will be acquainted to diffusion models, so you should know this picture pretty well. It's like when we are given with data and we know we corrupt the data with some forward SD that moves our distribution of pictures to normal noise. And then we would reverse this process, right, with the reverse SD. And that's why we learned the score function. We plug it into the reverse SD, knowing the drift in the diffusion term, and we are able to generate images this way, starting from the normal noise. And in this work, we were wondering about such a question: what if we don't have this information? Like we don't know what's the like the forward process that corrupts the images. So clearly we don't know the backward process as well. So the only thing we are given is a bunch of samples. And let's say we have like a black box that just yields samples on demand at different time steps. So we might even think that it doesn't corrupt the images completely. Let's say it corrupts part of the information, like removes color, and then it doesn't move the distribution, doesn't change the distribution to the pure noise. We still have some information, and we're not sure how to describe this process, but we understand that like the distribution changes, let's say in time. So here it's like time 0 and some time t capital, and then we would like to kind of like reverse this process in time. Despite that, like we don't really know what the process is, but we have access to samples at different, like at all the time points, let's say. And yeah, that's basically the problem setup. How can we? Yeah.
Could I ask? So, I guess two things. Are you going to assume that you have access to samples at different times, but of the same image, or always like different images? Like, can I sample this cat at both t equals 3 and t equals 7, or am I
No,
sort of
no. Like you give, so the interface is the following: you give the black box the time step, and it yields you some image or like some sample from this time step. It might be a different image with different noise. You don't know what it is, right? You just can like query with different times this black box, and it will spit out different samples, but they are not correlated in time. So you don't have access to any like trajectories or like conditional distributions. They are like completely I just here. So here I wanted to depict the process of corruption, because if they just like spit different images, it's not really clear on the picture what's going on. But yeah, that's the perfect question actually to clarify the process. We cannot we assume that we don't have access to the same image with different corruption levels. It might appear that like because it will yield the black box might yield the same image, but it's not guaranteed, right? It might yield just different samples.
so like it seems like I should sort of think about this as just being like a one parameter family of distributions. Are you gonna assume like some kind of smoothness or continuity or something? Like,
Yeah,
are you gonna
exactly.
assume that?
Yeah, it's like one parameter family of distributions, and it's smooth with respect to this parameter.
Okay, you are going to assume it's smooth and
Yeah.
in the parameter. Okay, cool. Cool. Thank you.
So, so we basically answer this question with our algorithm that we call action matching. And I would like to get to the algorithm. I would like to discuss some smaller problems and derive some simple equations on the way. And we'll start with the continuity equation, which basically describes how the vector fields shape the change of the distributions. And then based on this, we can approach kind of like the inverse problem. We can say that, okay, we observe some change of the distribution in time, or like in this one parameter, right? And then what's the vector field that does it to the distribution? What's the vector field that guides all these samples of the distributions? And so like with time, we'll converge to like a well-posed problem. We'll discuss some obvious problems of the inverse problem, like issues. And then we'll be ready to talk about action matching algorithm, which is like very simple. It requires just like a proper introduction, but the algorithm itself is very lightweight. And finally, we'll go to some applications, and we'll discuss biological applications, physical applications, because in many fields of science, we observe distributions changing in time, or like with some parameter, and so on and so forth. So, and then like after the talk, maybe we'll discuss more involved things regarding the math. So let's start with the continuity equation. And the continuity equation, so it's basically a very simple tool that does the following. Let's say we have some initial samples from a known distribution, like a standard normal distribution. And these lines are a vector field. So the vector field that drives all these samples individually. So they go along the vector field, and once they go, we see that the density of the samples changes, and we can ask like a very natural question: how does the density change in time, right? So once we know the initial distribution of samples and know how it changes, we can probably solve like a differential equation, or let's say like finite difference time method, and apply and like compute all the densities along the way, right? That's and understand like what are the densities here. So yeah, that's the question. We will quickly derive this formula for dqt dt. And for this purpose, let's say we measure some statistics phi and track these statistics. We measure it on samples, right? And see how, let's say, the mean or the variance or any other function changes with time over sample. So we say that we estimate the statistics on the current distribution of samples qt, and we do it like, let's say, with just like a Monte Carlo estimate. And then we can take the time derivative and the time derivative here. So statistics doesn't depend on time, but our coordinates depend on time, right? And we apply a simple chain rule. So we take the derivative of the statistics phi with respect to the coordinates, and then we differentiate the coordinates with respect to time. And clearly here, so, and this is the scalar product, right? And here, clearly, we see that this is simply the velocity, because that's what's given, that the particles, they drift along the vector field v that we have introduced. And now we can just say, okay, let's say we have like infinite amount of samples, and of course, this equation converges to the expectation with respect to the current distribution of samples. So stacking like things all together, we just said that like, okay, the derivative of the expected value of the statistics phi is actually this. And now we can like incorporate it, the vector field, into our equations. So starting from this equation, we can just expand it a little bit and write down the expectations as integrals over the space and take the derivative. So on the left-hand side, we'll see that the time derivative of the density will appear. And the right-hand side, it will be just another integral that we rewrite straightforwardly. And then we can take this integral by parts. We can just move this differential operator because we don't like that. We wouldn't like to differentiate the statistics phi. We want to move this differential operator to the other two guys, q, t, and v, and this like a simple trick, and we get this. And now we can note that this equation holds for any statistics phi. So we can take a delta function in some, or like a very narrow or narrowly picked function in some region of the space. So these guys have to be equal. Otherwise, we would be able to choose such phi that if they are not equal, at some point we can just choose a delta function at this point, and they can fail the equation. Right. So
just to get my grounding here, on the right hand side, the right box right now, that's the divergence, right? That's your notation for the divergence, or okay?
Yes.
Cool. Okay, cool. I just wanted to make sure I was reading it right. Cool.
Yeah.
Thank you.
Yeah, thank you for this clarification. This indeed like just the sum over all the first derivatives along the first coordinates, and yeah, here we get the continuity equation. So given the vector field and the density, let's say like we know the current density of the samples, we can evaluate the time derivative of the density, right? So we can actually predict how the density will change in the next time step. And the inverse problem would be that like we observe some distribution, we don't know the vector field, and we would like to guess what vector field does this job, right? Because like if we assume like there is some vector field that guides all the particles. So can we pose such a problem? So let's say we have a Gaussian just drifting in space to the right, and we might have access to the density or like to the samples. That doesn't matter. Let's say we know this histogram. Let's say it's a histogram, and we see this histogram drifting in space to the right. Can we understand what vector field does it? So to understand, let's look at several examples, but with samples revealed. We can see that, for example, these samples, they might all drift to the right along with the histogram, but also they can rotate around the center, for example. Another option would be is that they all drift to the right, and on the way they do these like weird Brownian motion or like just some random fluctuation that we don't know. And the key insight here is that just from observing the histogram of samples, we cannot really tell what's the vector field guiding it, because there might be many options, and we should somehow narrow down the family of the vector fields that might be doing this. So let's stick to the one that does the minimal job in some sense. So here we say, okay, if the Gaussian drifts to the right, then we shouldn't rotate the samples. We should all just drift all the samples to the right. Okay, and we can formalize it, and we can that's what we'll do next in a couple of slides. We are trying to formalize the notion of these like minimal vector fields, or the vector field that does the minimal job. We say that we consider all the vector fields that satisfy the continuity equation, right? So all the vector fields that yield the right change of the histogram, And then among these vector fields, we would like to have the one that has like minimal norm. And the norm here is just like the expected value of the norm of the vector field integrated over time, or we can say averaged over time. Doesn't really matter. Yes, Alex?
So, I mean, do you choose this sort of minimum? This would be, I guess, if I was looking for some kind of like physical intuition, this would almost be sort of the minimum. That's not even true. Why this condition and not others, right? Others I could imagine being reasonable would be to like minimize the energy of the flow, right? If I consider
Kind of the kinetic energy of the flow, right? Because like if we just integrate the vector field over all particles, and this is kind of like the average kinetic energy of all the particles.
Okay, good. I guess another thing is this going to always select like curl-free vector fields, or could you separately kind of specify whether the field is curl-free? Or
we will get to this in a second. Like
okay,
that
cool.
will be curl-free in some sense.
Okay.
There was another question, Jonas.
Yeah, I had the same question. Like, why not do the Helmholtz decomposition, get rid of all the, I can get the rotation-free field, but if you get to that, it's great.
Yeah. I'll get to that. So it's a bit harder to like formalize the Helmholtz decomposition in high-dimensional spaces. We would use the Hodge decomposition, right? And but here we will just see that in a minute we just like write down the Lagrangian of this problem as we do in just like in regular like optimization in the Euclidean space. So we just put like a Lagrange multiplier on our constraints, right, and minimize the objective. So we write down the Lagrangian for this problem, and then we can take the derivative of the Lagrangian. It's quite easy, but I just spare you from the like derivations, and we can differentiate these Lagrangian with respect to vector fields, and we'll get that the derivative equals to this. So this is the gradient of the Lagrange multiplier, and Lagrange multiplier here is a function, right? It takes x and yields a scalar. So we take a gradient, and since we want our vector field to yield the optimum of this optimization problem, it has to be a gradient flow, right? So this derivative has to be 0. So the vector field has to be a gradient flow, right? And this is the like key takeaway message of like this like problem setup, that okay, to define these like minimal vector field, let's take a function. Let's start like saying that like we can parameterize a function st, right? And that takes a high dimensional vector, does some transformations, it yields a scalar, and then if we differentiate the output with respect to the input, we'll get a vector field that's from these kind of like family of minimal vector fields. And we also can say that it's unique, but we can get to it like maybe after the end to a simple proof that it's unique. So far, we'll just take it as given that there exists like a unique vector field that drives the histogram. So in some sense, I want to say that the problem is already well defined, and we can move on to the algorithm. We can say that there is a unique nabla S star such that the continuity equation holds. And so we are left with like several steps, and these steps are very easy. We can just say, okay, let's just minimize L2 distance. So we parameterize some function st with a neural network, or like, yeah, let's stop at the neural networks. So we parameterize some function st, and we would like to minimize this L2 distance. So it's an expected difference, expected like L2 norm with respect to the current distribution QT. And nabla star is our target, right? And we also integrate it over the time. So if we are able to minimize this functional, then we clearly we'll clearly get nabla S star, which is our goal. And the problem is well posed because there is such a vector field and it's unique. So we'll just open the brackets, and since we minimize with respect to S, we'll clearly see that the last term, which doesn't depend on S anyhow, we can just get rid of it. And the first term, it depends on S, but it doesn't depend on nabla star, so we don't have problems with it. So the problems we have here were like this term mixed. But we can note that these two guys, they are almost like from this, like here they are together. So we can use the continuity equation to get rid of them. And just like a couple of integration by parts later, we will arrive at this functional. So this, our objective, initial objective, is equivalent for like optimization to the following one. And the last step, just to polish a bit the result, we will get rid of the integrals and we'll write down them as expectations. Okay. So now we can clearly see the following thing, that like once we parameterize some function S with a neural network, and we have an access to the samples from the distributions Q0, Q1, and Qt for any t from 0 to 1, we can estimate this functional and we can minimize it, right? So how would, yeah.
So sorry, yeah, could you go back for a second? So and here like S0 is S at t equals 0 and S1 is S at t equals 1,
Oh,
right?
yeah, thank you for clarifying.
And then
S at t equals 0, S at t equals 1, and here it's S of t current t.
So the other thing I wanted to run past you is, I mean, yeah, it seems reasonable to try to minimize the L2 loss, and you know that there is a solution, so minimizing that, we'll find it. But then as like a divergence, I guess, you know, if you don't get there, like an alternative I could imagine, I'm sure it's probably less tractable, but it feels like I could try to find the flow that if I act with the flow, it minimizes the KL divergence to the true distribution. Do you think that that's going to have like a fundamentally different flavor? Do you think that that's like horribly intractable, or do you think there's a chance that you could try to change the divergence for the search to bias it towards?
So like, so far our common like intuition with the co-authors is that this algorithm relies heavily on the geometry of the Wasserstein space of distribution, and it's related to this. So it's kind of like natural to minimize this, because we'll see that like after the end of the talk, we will go like as a bonus slide to these like Wasserstein geometry of the distributions, and we can see that like that's actually trying to recover the like vectors from the tangent space on this manifold. So the KL, I think that like we might make an analog with the KL, especially like if we somehow manage to put like Gaussian distribution there and maybe these like L2 appear, or but in general, yeah, that's kind of like that we don't go deeper into this in our work, and we are not actually sure if it's possible to minimize different distances. So from our perspective, it seemed like more natural to do this. Yeah, but
Cool.
So so how does one learning iteration look like? Just to be clear, like once again, like we talked about like once we have this histogram, but what it really means, we assume that we are given with samples, as we discussed on the very first slide. We have a black box that we can query with time, and it will yield a batch of samples, uncorrelated, independently distributed, just from this like marginal, right? So we query it at time t0 and we'll get a batch. We query it at time t equals 1 and we'll get a batch. We query it we sample times uniformly, and we query with these times, and we'll get a batch. And then we put all these batches into this loss. We parameterize function s. Once again, that's s at t equals 0, s at t equals 1, and st. We parameterize it with some parameters theta, and we can estimate, we can do a Monte Carlo estimate of this loss. And these guys here, they depend like only on the boundaries. And this guy here, it depends only on what's in between, right? And we can see that, yeah.
I guess just looking at the loss, what stops like S0 and S1 from being arbitrarily large or small or whatever? What constrains the?
That's.
Are there any constraints on the S?
Yep. That's right now. Yeah, so we see that like this loss actually tries to set S0 as small as possible and S1 as big as possible. But then there is like intermediate term, which actually does this regularization on the acceleration of these particles that they'll shoot. So if you write down the ODE that guides the particles from the continuity equation, and you'll write down the acceleration, something like this will appear. Like minus nabla, this is the acceleration. So that stops us from learning just like arbitrarily high and low s at the boundaries. And at the same time, it stops us, like they kind of like balance each other, because if we just minimize this, it also won't work. So yeah, we put these like our like the gradient of this loss we can estimate in our favorite optimizer that spits the next parameters, and we're done. That's one iteration of the algorithm. And note that here we use only access to the samples. It's completely model agnostic. We've never used any information what's the forward process, what's the backward process. It's just we take different samples at different time steps, we put them into the loss, and we run it. And the question is then, how do we apply it? And we have already touched it a bit.
Before you go on, could I just can you go back a slide? Make sure I kind of have the right checkpoint. So, okay, you had a black box. The black box is a one parameter family of distributions. You kind of set a t and you get a sample, but otherwise you can't ensure any correlations or anything.
Yeah.
You're going to try to learn this thing. You convinced me that there is a unique minimum energy gradient flow that will kind of match the one parameter family distribution, assuming there's continuity. The way that you learn it is this objective. Now, I guess like the type of this S thing. So this is a neural network that takes as input the kind of whatever dimensionality of my space is, and t, and it's a scalar function of both of those. And it looks like, as far as evaluating the loss, now you just sort of generate 3 batches, one at t equals 0, one at t equals 1, and one at some intermediate time. And the only things we need to be able to do is a forward pass of s at 0, s at 1, and we need to be able to evaluate, I guess, the gradients of both arguments of our little S neural network, right? We have to take gradients of t and gradients of with respect to x, and that's it. And then we plug it in and we go, and we're good to go.
Yep. Yeah, that's absolutely correct.
Excellent. Okay. So it's a scalar function. S is a scalar function, a neural network that eats an x and a t and spits out a scalar.
So we discussed that like our vector field is a gradient flow, right? So we parameterize S as a function that takes our state sample, right, from the state space as an input vector, and outputs a number, just one number. And we don't restrict it anyhow to only positive or to only negative numbers or to normalizable as like we would like in energy-based models, or like something like this. We have no restrictions. We just yield these numbers. We take the derivative with respect to the inputs, which we denote as nabla s. We take the derivative with respect to the time, which is also another input. And we get these derivatives, we plug it into the loss, and we can estimate the loss, and then we can take the gradient with respect to the parameters of these functions as.
Yeah, and in terms of cost, it looks like this is 2 forward passes and 1 backward pass through a scalar neural network. Maybe 2 backward passes. So
Yeah.
two forward passes, 2 backward passes through a scalar neural network. That's it,
Yes.
right? Awesome.
So,
but if you're taking a gradient of this loss, now we have second derivatives, right? But those are gradients with respect to the parameters. So,
Yeah.
okay, so you've got a scalar neural network that has 2 inputs. In order to evaluate the loss, we need to do 2 forward passes and 2 backward passes through that 2 argument function, scalar function.
so
But then to take the loss of that, we have to take
one backward pass.
What's it?
The differentiation with respect to x and t, it can be done via 1 backward pass, right?
Sure. Yeah, the 2 arguments at the same time or whatever. Yeah. Okay. But then we need to. So it's an otherwise there's no constraint on the output scalar, but it does need to be differentiable in both arguments.
That's
I guess at optimization time, we're taking. We need to be able to differentiate this whole thing with respect to the parameters. So whatever the relationship there is has to be.
Yeah, of course.
Okay,
Yeah, in that sense, it's heavier than models that just output the vector fields right away, right? But we will still show that it's pretty scalable.
Thank you.
Yeah, and then like to apply this stuff, we just have to follow these vector fields. We just solve an ODE. So like namely, we start with x at time 0, and we can run the earlier method or any other method for ODEs. And here we also do we do the forward parse, we do the backward parse, we get our vector for this exactly sample, and we update the sample, and that's it. So let's look at some examples. This is like a very toy example, but let's say that we have this data. Once again, we don't know what's the process that generates these data, and we have these like snapshots. We have more data at any time t, but I just visualize these snapshots. So we learn our function s on this data. Then we sample data at the initial time t0, and then we run our ODE for all these samples, right? So, and we can take a look at the generated data, and we see that it's steps by step. It generates like right marginals, and that's the only thing we can like guarantee here. Really, we cannot guarantee that we recover exactly the ground truth underlying mechanism behind the data, because we just show that like it's an improper task. But what we can guarantee is that we can learn such a function that we take the data at the beginning, and then we propagate it, and we'll match all the marginal distributions, all the snapshots, and you won't distinguish it from the data. And
I guess, but this is a little weird, right? I mean, this doesn't, at least as described, this doesn't seem like it has a whole lot of utility, right? Like most of the time, I think you'd want to go the other way, right? You have some corruptive process, you have some one-dimensional things, and it might be easier, or I mean, like usually we're interested in doing generative modeling or something, right? So I might imagine like in a diffusion model, I've got clean images and I've got some kind of corrupting process that's parametric. And I'm most often interested in drawing a sample from t=1 and running it backwards. And you certainly can do this here, right? You can run the evolution backwards. Is that as stable as running the evolution forward? Is there any sort of issue with?
No, there is no difference. Here we can assume that just like noise is at t=0, and here the generated images is t=1. Of course, it's completely invertible, right?
But then I guess the only kind of concern I would have is if I was actually using this to try to draw samples. Certainly, if I imagine I had access to your black box, I could request a sample at t=0 or t=1, and I could evolve that, and I could sample from the correct marginal at t=0 or t=1.
Yeah.
But if I drew a sample at t=1 and I just ran your evolution backwards, and if your thing actually learned a minimum energy flow, then like I guess all I'm going to get is whatever the kind of correct t=0 sample was for that particular t=1 output, right? Like I won't have any diversity in the sampling process.
No, why? Like if your marginals if it depends on the process. If you had like trajectories and then you removed the information about the time correlation, then probably yes, you would recover these exactly samples. But if you just have independent samples and you are not really sure, like, so you can like kind of move the samples between the snapshots, and they might be different, right? But the marginal would be corrected because the ground truth samples, let's say they come from different trajectories. You don't have the same trajectories here, right? And that's actually the case in biology, for example. So here the data is these like scatter points of different color, and different color corresponds to different times. And what we actually have like data for different for several time steps. We don't even have the dense data, and it's called like a trajectory inference for population dynamics. So it's like a dynamics of cells. So here is like a toy task that's which goal is to like simulate what's happening, because like the real data is hard to visualize. But on the toy task, we can see that like we are given with like several snapshots, and we can recover then like meaningful trajectories of these samples. And once we have new data from at time 0, so let's say we built such a model, right? And once you have in new data at t=0 a cell, you can predict up to some level, like in terms of distributions, you can predict how it evolves, right? That's what it does.
I guess the one thing that it strikes me as a little, I mean, the resulting evolution that you have is deterministic. So if you had a new sample at t=0, like it feels like there's two ways forward. If I wanted to, I could invest some effort in doing density modeling for one of the two marginals. And at that point, I have like a legitimate generative model, right? I could, if I modeled the marginal at t=0, I could run the whole thing forward, and I have a sort of joint distribution at every intermediate step. If I wanted to model the marginal at t=1, because I thought that was easier, I could do that independently, draw samples from my model of the t=1 marginal and run it backwards. But if all I did was now observe a new data point at t=0, you could try to make predictions about where it's going to go, but those are all like deterministic predictions, right? There's a single trajectory. There isn't a stochastic trajectory. So you're not predicting like a distribution for where it might be. I mean, you're committing to a particular prediction, but like it feels like there's less utility in saying like, oh, I think it's going to be exactly here, than saying there's no diversity in the evolution process. All of the stochasticity is coming from the marginal itself. So once I observe a t=0 sample, like everything is kind of determined after that point, right?
So I don't discuss it here because it would be too dense. But we have several like versions of the same algorithm, and I described the deterministic version, which is just to convey the general idea of the framework. But we also have another version which is stochastic. So instead of like we say we want to find like an SD pretty much that does the same, and there like you can control these like stochasticity. And here are the pictures. If you I don't think I can like zoom in here, but these trajectories are actually stochastic, and they are generated with the stochastic method. So another version that can like teleport kind of mass, it can change these weights of samples on the go. And these might be also interesting for some niche applications. But I think the main kind of answer for your question is that it really depends on the prior knowledge about your data. If you would like to move, so the idea behind like all these three methods is that we learn infinitesimal like optimal transport. So between these two snapshots, if we would learn the algorithm that I just described, these like action matching, we would learn an optimal transport. So if we do the stochastic version, we learn the Schrödinger bridge between these two. And if we then like unbalanced optimal transport if we allow for these like mass teleportation. But the main answer is that if you have some prior knowledge about what's happening to your data, or you have some desired behavior, you can incorporate it in one way or another. And if you would like to get a distribution of like trajectories, and you have like some drift or no diffusion term on mind, then you can do it as well. And this actually, the algorithm doesn't change pretty much. You'll have another derivative there in the loss, but the rest stays the same, and the concept stays the same.
It's interesting. Yeah. And I mean, I also don't think it's out of the question to model. I mean, I guess I keep thinking back, I mean, you invited it to the first slide, but thinking back to like diffusion models. And if I wanted to use this to replace diffusion models, like I could build a forward process on images, which is just Gaussian noise. And I could try to learn using your method to transport. But then I also am perfectly willing to model the marginal at the end of the diffusion process, because I can just assume it's Gaussian. And then I will get a whole kind of diversity. And even if I have sort of a deterministic map from the sample from the marginal, I don't care anymore, because I still get, like, I'm drawing independent samples at t=1.
Yeah, let's just, I would like to show one more like applications in physics, and then we'll get to the generative models, and then probably discuss it there. So here it's, I just show you the histogram of the training data that we have. And the histogram changes in time, and these are like 2D projections of a 3D distribution. And the distribution is the...
Are these supposed to be like orbitals or something? What is this?
Yeah, that's like an excited state of the hydrogen atom that kind of oscillates in time. And like we can recover these data with like, we can make the same like histograms, like starting from the time 0. So we basically can take a quantum system where we don't have any notions of trajectories, right? And we can measure these quantum systems in different positions, and we can recover the dynamics of this system. So we can build a model of it.
Can you check, I mean, for this case in particular, does the dynamics correspond to a semi-classical dynamics for the quantum system? Or is there, like, what is there something you can compare against, kind of a theoretical ground truth, like a semi-classical method? Or
oh no, yeah, for the hydrogen atom, we can solve it analytically. We know that's how we did this experiment. I just run the classical, like the Schrödinger equation that I know how to solve analytically. I sample particles, I collect the data, and then we compare it to the ground truth. Yeah. So
I guess maybe I'm a little confused, but the simulation here was like you had a time varying Hamiltonian or something, and you're showing me samples from the ground state of the time varying Hamiltonian. That's the histogram. That's the movie, right?
No, the Hamiltonian is stationary. It doesn't change with time. We just start with an excited state, but not the eigenstate. It's not stationary.
Okay. Okay,
Yeah.
so it's just evolving. Okay, there's a fixed Hamiltonian that is evolving under time, under Schrödinger's equation.
Yeah.
Okay. Thank you.
Yeah, and as we discussed, for generative modeling, we can do generation from like noise and like generate images, of course. But then we thought that like maybe for some niche image applications, it would be interesting to start with like some closer images to the ground truth, and we can like input the whole vector and we can do it like in the case where like our conditionals, if we want to do like, let's say, conditional generative modeling, we want to do it even in the case when we can like, okay, for colorization we can actually kind of disentangle these condition and the variable. But here we pretend we cannot. We start with some like grayscale images, and then we evolve to the image. And we cannot really like it's not like properly defined. Like we cannot write down equations for this process, and we cannot understand how to reverse it, because the reverse process would be the colorization function, right? And then like we can learn dynamics such like this. And in terms of generative modeling, you're right. Like if we just do generation, we can indeed like choose a prior, like we can start from a normal noise and anneal to the image. But we were wondering maybe it makes sense to start from a different distribution for something which is like closer to the original image, so we do less job on generating the image. And yeah, here are the results. So we compare to the baseline, which we like, where we pretend that we don't have any information about the process. So we can learn the scores of the distribution still, right? We can take the same network, we can learn the scores with the slide score matching or score matching, and then we can use these scores. We can plug it into the Langevin sampler, right, and just use it to sample from different distributions. But that would be much worse than our algorithm. And our algorithm, it doesn't perform as good as diffusion models from the paper where I took the picture of these with the stochastic differential equations. But visually, it performs quite well. Like we can do like a pairwise comparison of the images if we start solving ODE from the same noise values. So we wanted to show here that maybe like we don't expect this to be like image generation, that the image generation is the main application of our approach, but we would like to show that it scales. And images here are very good because we can like visually validate that our method scales and yields like good samples. Because if we go back to the like bio applications, there we compare with methods that doesn't scale to images high dimensions, and that was kind of a statement. Yeah, and then colorization and superposition. So colorization is done basically like this. I just took some samples, and you can learn it like pretty easily and pretty fast. That's you go from the grayscale images to the colored images. Yeah, and as we partially discussed here what's in the paper, and we'll upload the new archive version soon. But in general, you can see there are these like stochastic version that I've mentioned, where you learn an SD instead of OD, and the loss is pretty much the same except one term. And you can see the unbalanced version that allows for the mass teleportation and changes the weights of particles while solving the OD as well, or SD. And methods, we put like detailed derivations, and also a link to the JAX implementation for images. Yeah, I have a couple of slides that we can like discuss uniqueness, these Wasserstein things, if you would like. I know.
Well, this is really cool. Yeah, I guess now I'm just trying to think, like, trying to compare your method to diffusion if I was interested in doing generative modeling. And it feels like, so on the one hand, you have a lot more freedom than most diffusion models. I mean, I know there's been work, but you're kind of agnostic. I mean, there's both a bug and a curse or whatever, right? In the sense that you are completely agnostic to any structure in the forward process. You have a lot more freedom if you wanted to do modeling to come up with arbitrary kind of forward processes. But that's also a potential downside in the sense that your model or your method is agnostic to whatever you're not utilizing any structure in the forward process. So it feels like compared to ordinary Gaussian diffusion, in Gaussian diffusion, the forward process is fixed. You might take issue that it's simple, it's just Gaussian noise. But the learned score, the model makes tremendous use of the fact that it knows a great deal of structure in the forward process in order to improve the learning of the reverse process. So I guess, here you were comparing numbers, but is there a difference in, like, I would expect a difference in the time it takes to train and stuff? Like, is your method take a lot more steps or a lot more gradients or a lot more data, a lot more batches to learn a decent generative model compared to ordinary Gaussian diffusion, or is it comparable? Or
here we compare all the numbers with the same amount of data, with the same architecture, with the same number of like batch size and so on, with the same hyperparameters. But it does take more time because of these, like, one iteration we have to backprop, right? And this contributes to the time of learning, and it learns slower because one iteration costs more. But this difference, I guess that, like, on a huge scale, like of more than like state-of-the-art generative models, it really matters. But if we speak about these scales, it's pretty much the same.
cool. Yeah, so
we thought more, like, indeed, in generative modeling, you can build any process, but there are, like, we thought more about, like, applications to natural sciences. Like, you observe some physical phenomena and you would like to understand what's going on. Like, you want to build a model of this, like, quantum system evolving in time, or you can take some data, like, of like sociological data or like biological data, and you have, like, snapshots of distributions, and you would like to build a model how this distribution evolves in time, and maybe even, like, predict how it evolves. Yeah. So maybe for some image applications, we don't really do image applications or image generations. Yeah.
Well, but I guess, like, I guess why not, right? Because it feels like, if I wasn't just doing generative modeling, let's say I am willing to model a marginal, like, the whole point is, modeling t equals 0 for any sort of, modeling images is hard, and it feels like diffusion models are successful because they manage to take a hard to model distribution, the image distribution, and turn it into an easy to model distribution, along with, while following a process that's easy to reverse. And, like, you can benefit in much the same way, right? Given a complex distribution, one that I guess, like, so do you have any just, like, density modeling comparisons? Like, if I interpret this as a method of density modeling, is it kind of competitive in terms of likelihoods? Do I have tractable likelihoods out of this thing?
Yeah.
It feels like I ought to, right? If I
you can evaluate the likelihoods just since you have the vector field, right? You can evaluate its divergence and then, like, solve it as well as in diffusion models, so in, like, normalizing flows.
Yeah, like, I feel like a real benefit here would be there's lots of other domains where I'm interested in doing density modeling for complex distributions, but where I don't think that just independent Gaussian noise is a good destructive process, but I could come up with destructive. Like, what about text, right? Like, there's all kinds of ways I can know to make text easier to model. I could start scrambling words or something and start making it uniform, or some, make it look like a Markov model. It's easy to model, and then, like, try to undo that process. Is there like, I guess, like, I'm wondering, like, maybe are you underselling the method a little bit in the sense that, or like tabular data is also rich and hard to model, but I can imagine all kinds of, easy to simulate forward processes that could destroy all the structure in tabular data and make it easier to model the marginal. Is there anything, I guess, like, this is you're kind of restricted to continuous settings rather than discrete ones, right? Because you need continuity.
So we have some ideas how to, like, actually with these, like, unbalanced versions, how to increase the scope to discrete data, because then once we have these, like, mass teleportation property, we don't restrict ourselves to moving all the mass only with the vector fields. we can just like increase mass in some points and decrease. So we can actually model, like we can kind of build a bijection between continuous domain and the discrete domain, and then solve it in the continuous and then go to the discrete. So
Yeah,
that's possible.
No, yeah, I wonder, yeah, for certain, I mean, there's lots of tabular data where the actual, points are continuous or can be treated as, but there's structure in the, the tabulation or the rows or the columns or whatever, or hierarchical relationships. And I don't know. I don't know if people have just thrown diffusion models at those. I don't know if you did, if they'd be very successful, but I mean, you guys could certainly easier to throw action matching at tabular data than it would be diffusion.
Right? That's kind of like the whole point, I think, of like it's quite easy to learn, and it's very general. So you can try this thing on many different tasks.
All right, so okay, I'm feeling great about it. This sounds wonderful. Sounds like the best thing since sliced bread. What are the problems? Why is it? What's the downside?
I mean, the downside is, of course, that's it's like the iteration. One iteration costs more. The other downside, which is kind of like the lack of our knowledge, because like people have developed a lot of like architectures that are they developed a lot of architectures that yield the vector field, but the architectures that yield like a number, we don't know such, like a lot of them. So we found like one little workshop paper about this question, and that's what we basically use. But we cannot just put like a UNet, right? Because like in our objective, we also have to use these like scalar outputs, right? And that's another interesting question. How to thank you, Ryan. So that's another interesting question. What should we choose as an architecture? Because it's not really clear. So far, to compare, we just like took the same architecture, and that's pretty much it. And like the same hyperparameters, same architecture, just different laws, and we showed that it works. But there are like a lot of space for improvements in different things.
Yeah, because I know on the diffusion model side, even though, I mean, the score function you could parameterize as the gradient of some scalar function or whatever. But my impression is when I talk to people who tried that this just leads to worse results.
Yeah.
Now, I wonder, so why don't you also relax that constraint? Why don't you use something like a UNet? As you point out, you also need to model the boundary terms. But what if those are just also sort of independent networks and we somehow impose a constraint that they should?
Yeah, we just haven't
they should
tried
approximately be the right boundary term.
Yeah, that's kind of, but then like we have to put some regularizers that match these networks to this network and so on and so forth. But that's possible. Yeah, of course.
If it leads to even better results, then it might be worth it.
But that's true. So
but there is an elegance in learning the scalar function. That feels nice.
Also the choice kind of like might be restrictive in that way that like if we like heavily rely on so we know, for example, like that if we just solve optimal transport, we can reach the target in one step, right? And in that sense, like if you rely on the models that with some like normal noise, let's say, like with the diffusion, right? You have to integrate along this path. And so here we, first of all, like we kind of like solve these like infinitesimal transport too. So we expect this, like you can easily solve it easier. I haven't benchmarked all the ODs in terms of number of steps, but we expect that the trajectories will be kind of like more straight. But I'm trying to say that restricting your like path in terms of distributions between the target data and the prior might be not always like favorable for generative modeling. And we thought that maybe just like relaxing these conditions on the path might like via our algorithm might help to the field.
Feels like another way to get out around that is you could just augment the space, right? You could add more random variables on either end of the flow, and that would let you untangle, or add more dimensions, and then you don't get tied in knots.
So like our intuition, I think that like it's better depicted in this picture, that we have some, like, let's say, initial distribution and the target distribution, and we like diffusion defines some weird path that we don't really know exactly how it looks like, but let's say it looks like this, and then there is like a straight line in this space of distributions, which is the optimal transport. And then just given this freedom to this point and this curve, we might be able to solve some problems better for generative modeling. And this is the picture for the stochastic key. So here the equation has these like stochastic term and these like growth term, and as we discussed here, you can have like multiple paths. So that's, I think, like our main intuition, and also because this picture kind of like motivates why the loss should look like this, because the path is, we assume that the path is drawn on the manifold of distributions, and we actually learn the vector fields from the tangent space. So these the gradient flows, they form the tangent space on this Wasserstein manifold, and you basically have to learn one vector in the tangent at every point, and you do it with like L2. Yeah.
Very cool.
Yeah, maybe I can add something. Hi, Alex.
Hey.
So, right, in response to your question at why did we pick like a minimizing kinetic energy, I mean, as Krill pointed out, it is the solution to infinitesimal optimal transport. So, like, if you want to go from one distribution to the next that is infinitesimally close, so basically our method finds the vector field that is identical to what optimal transport finds. So
yeah, and I mean, I guess that's fine, except optimal transport is parameterization dependent, right? So like if I sent the space through a bijection, the minimum energy transport is going to be different if I transform the space than it is if I don't transform the space, right? There's a parameter dependence there.
Yeah.
So then that just like I mean, optimal transport, I think, is I don't know. It feels like a good principle to guide you, but I think it relies on having a good set of coordinates for the space, because otherwise,
Yeah, that's true.
And like,
yeah.
So, but then once we start talking about modeling like images or something, you're saying something about minimal transport is about moving a little bit of pixel mass from one pixel to another, and I'm less convinced that that's the best guiding principle for image modeling.
That's kind of like another question. Let's say we have these like action matching tool, and then we can like map everything. So we have like these defined, let's say, diffusion on the space of images. We can map everything to another space where L2 does make sense, right?
Yeah.
And then we don't know what the process is there, so we can learn it with action matching.
Have you tried that? I mean, I guess is there anything that goes wrong in the objective if I just stick a bijection at the front and end? Does everything still work?
It shouldn't be, because like you'll get some like distributions in another space. You solve the problem there, and then you clearly can map the tangent vectors, the gradients for like the vector field from your space where you map to. you can map it back to the original space, right? These tangent vectors.
Yeah, this sounds like an intriguing option, right? In the sense that like latent variable models are really nice. I mean, philosophically, because they kind of separate. Some of the modeling is done in the latent space, some of the structure is defined in the latent space, and then the rest of the structure is sort of defined by the decoding process or whatever. And so you get to draw a line in the sand, signal and noise. I care about this, I don't care about this. And like things like flows, they try to model everything. And diffusion models try to model everything. But like I feel like what you just said, if you learn a bijection at the beginning and at the end of the process, then now you've done the same sort of separation, right? The initial bijection would try to undo all of the structure you don't care about and somehow map the space, map the images not to a pure Gaussian, but to something that you've eliminated all of the structure I don't care about, right? Where all the leaves are in the tree. And now you left with something with structure, and you learn a process that destroys the remaining stuff that you actually care about, the stuff that you care to model. And then you're left with something that's simple again. It feels like it would allow you. It gives you another lens to slice the space.
Yeah, I think that's a good thing to try. Thank you.
But it also feels like you'd need to control it in some way, right? You need some mechanism, either like some sprinkled in some Lagrange multipliers here or there. But you need something to tell the model how much it should try to model in the bijection and how much it should try to model in the flow, right?
Yeah, that's true. That's true.
Anyway, very cool stuff. I enjoyed the talk. This feels like a new thing to keep in your toolkit. This seems great, and it seems thank you
Thanks
very much.
for inviting me. It was a pleasure to present.
Yeah, very cool.
Thank you.
Bye, guys.
Bye, guys.
Take
Thank
care.
you, Brian.